All right, how's it going, guys? Let's jump into 6.13 improper integrals. Please recall that a definite integral is an integral from a to b of f of x dx. And by the fundamental theorem of calculus, the first lemma, this becomes the antiderivative of b minus the antiderivative of a. Now, when we're dealing with improper integrals, what makes these definite integrals improper is if a or b is infinity. So we're integrating from negative infinity to some number, or from some number to infinity, or both, right, over the entire domain. Okay, so that makes integral improper. If direct substitution gives us an undefined. So in this first example, we see 1 over x. And I've given you the graph here to show you that there is a vertical asymptote at x equals 0. So as the limit as you approach x equals 0 from the right, this function increases and never stops. Okay, so you might think as we approach from the right, since our function increases infinitely, you might think that this area underneath is infinite, but there's not really a way to eyeball it. So what we're going to do is we're going to use a definition of limits. So I'll write this down. Um, if direct substitution of a or b into f of x is undefined. Okay, so plugging in 0 here will give us 1 over 0, which is undefined. Plugging in 0 here will give us 1 over 0, which is undefined. Same thing here, plugging in 0. Natural log of 0 is undefined. And if you notice example 4, we have condition 1, where our b value is infinity. So to solve these, we're going to use limits. We're going to say use the limit as some number approaches infinity or negative infinity, or in this case, the limit as some number approaches 1 or 0, or wherever the excluded value of f of x is, wherever we have an asymptote or a hole or some kind of discontinuity. And then we're going to use our limit knowledge to solve that. So before we jump into these, I'm going to quickly remind you a couple important limits. So the limit as x approaches infinity of e to the x is infinity, but the limit as x approaches infinity of e to the negative x is really 1 over e to the x, which is 1 over infinity, and the limit as x approaches infinity of 1 over x is 0. So let's go ahead and look at example number 1. We have the integral from 0 to 1 of 1 over x dx. So we know that using our integration rules, this should equal, well, the integral of 1 over x is ln x. So we're solving natural log of x from 0 to 1. Now, we can plug in 1 into natural log of x, no problem. Natural log of 1 minus. Now, when we plug in 0 here, we're going to get natural log of 0, which is undefined. So what we're going to do is, instead of writing natural log of 0, we're going to use a limit statement. We're going to say take the limit as some other number. I'm going to say capital B. I like B. I've seen it in very many textbooks. The limit as b approaches 0 of natural log of b. And the limit as b approaches 0 of natural log of b, that is negative infinity. So we have natural log of 1, which is 0, minus negative infinity, so plus infinity. So essentially this area from 0 to 1 underneath this curve is an infinite area. When that happens, when our area is infinite, we say that the uh, integral diverges. Okay, So if our area is infinite, we say the integral diverges. This could be positive or negative infinity. Here's a little experiment for you guys. Using this logic, what can be said about the integral from 0 to 1 of 1 over x to any exponent p dx, given that p is greater than or equal to 1. Example number 2, this one, you would assume that, the same limits from 0 to 1, 1 over square root of x, because this still increases uh, to infinity as we approach 0 from the right, you might be inclined to say, oh, this diverges too, but we have to be sure. So let's go ahead and solve this integral. I'm going to quickly first rewrite this integrand as x to the negative 1/2 dx. And now we can take our integral using power rule, add 1 to the exponent, and divide by that new exponent. So x to the 1/2 over 1/2. So this becomes 2x to the 1/2, integrated from 0 to 1. Now, when we plug this in, we get 2 times the square root of 1 minus 2 times the square root of 0, which is, well, just 2. This does not diverge. So the area underneath this curve here is 2. We didn't have to use a limit here because square root 0 is a number. Let's look at the third one. Natural log of x. Now, I gave you this question to see if you can remember how to find the integral of natural log of x. It's not 1 over x. That's the derivative of natural log of x. Um, Pause the video now to see if you can remember how to solve for this. Okay, so we're going to actually solve the integral of natural log of x. We're going to solve the indefinite integral first so we can write our antiderivatives. So to find the integral of natural log of x dx, we actually need to use integration by parts here. Okay, this is one of the first integration by parts questions. Following Lyatta, the natural log of x is our u value. So du is 1 over x dx. dv is just dx. So it means that v is x. So using the definition, uv minus the integral of v du, uv would be ln x times x. So we have x ln x minus the integral of v du. So that's x over x dx. These x's cancel, so this becomes just 1. And the integral of 1 dx is x. So we can rewrite our definite integral from 0 to 1 as x ln x minus x from 0 to 1. Now let's solve for 1. So we have 1 times the natural log of 1 minus 1. And the natural log of 1, you should remember that that's just 0. So this whole term goes away. This is 0 minus 1, which gives us negative 1. Minus, now we're going to plug in 0. So it's going to give us 0 times, and the natural log of 0 is undefined. It approaches negative infinity. So we're going to use our limit statement. Limit as some number approaches 0 of natural log of b minus 0. Now, 0 times anything is 0, even infinity or negative infinity. And to prove that, you can conceptualize just picking larger and larger and larger numbers forever. Each one of those numbers times 0 will give you 0. So we have negative 1 minus 0. So our answer here is negative 1. Question number 4. Now this comes from a college level probability course that I tutored. This is called the exponential probability distribution formula, where in this case our lambda value is 2. I figured. So e to the negative 2 x. You could use a u substitution. So let's let u equal negative 2x. That means du is negative 2 dx. So we can divide both sides by negative 2. So du over negative 2 is dx. So this becomes the integral of negative e to the u du. And the integral of e to the x is just e to the x. So the integral of negative e to the u is just negative e to the u. And let's remember that u is really negative 2x. And we're integrating from 1 to infinity. Okay, so let's plug in infinity. Because infinity is not a number, we're going to use our limit statement. Now, on the AP exam, they want to see that you use this limit statement, right? I know you understand the shorthand negative e to the negative 2 infinity. I know you understand that shorthand means find the limit, but they want to see the limit statement. So we're going to write it out. The limit as some number b approaches infinity. You could have written it here, or if you'd like, you could write it here. The limit as b approaches infinity. Both work. Okay, so I'll write this as infinity, but we're really plugging in b to limit as b approaches infinity of negative e to the negative 2b minus negative e to the negative 2 times 1. So we're plugging in infinity here in this limit statement, applying the fundamental theorem of calculus, and finding the antiderivative, which we already have, and plugging in our lower limit of integration here. Okay. Just a little clarification. This minus minus, let's just change that into a plus. E to the negative 2. Let's rewrite that as 1 over e squared. And let's rewrite this as negative 1 over e to the negative 2b. Now, as b approaches infinity, this exponent will approach infinity. So we have negative 1 over e to the negative infinity. And one of the first limits that we reviewed was e to the negative x. As x approaches infinity, this converges to 0. So we can replace this term with 0, and we get our answer 1 over e squared. Okay, please do not put boxes around your answers on the AP exam. I'm just doing that here to show you uh, what the answer is in case you fast forward it. Okay, so I've pulled up CA2 from the improper integrals 6.13. I already did them, so I'm going to erase them and do them again. So we want to find the integral. Let's first rewrite this as the integral from 0 to 5 of 5 minus x to the negative 1/2 dx. Do a quick u substitution. U is 5 minus x. That means du is negative dx. So let's rewrite this as the integral without limits right now because we're using u temporarily. So it's going to become negative, because du is negative dx, negative u to the negative 1/2 du. Power rule tells us u to the negative 1/2. We add 1, so that gives us u to the 1/2 over 1/2. So I'll keep that negative 2 u to the 1/2 there, and replace u back with 5 minus x. So we can rewrite this as root 5 minus x. Now we're going to plug in our values 0 to 5 and substitute. So the first value, negative 2 times the square root of 5 minus 5 minus negative 2 times the square root of 5 minus 0. Okay, 5 minus 5 is 0, so this entire term cancels out. Here we have a minus minus, so this becomes plus or positive. 5 minus 0 is 0, so we have 2 root 5 as our solution. Let's check the answer key. Yeah, 2 root 5.